world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this.
All right, hello and welcome to Ether Cosmology Research and Reading Night. Tonight we're going to be doing some reading from a book called Interference, The History of Optical Interferometry and the Scientist Who Tamed Light. So we're going to read from chapter 3 here about the birth of interferometry and kind of get a history lesson on what went down with interferometry and how they came to the understanding that they could use light to measure velocity. So without further ado, I'm going to go ahead and lead us in. And then if anyone wants to take over, I'll popcorn out or whatever. All right, so at light speed, the birth of interferometry. Arago had more ideas by himself than a full generation from our boy Foucault in 1853. Open your eyes. The world goes from dark to light as reality presents itself to you in a flash of awareness. Distant objects touch your eyes as light rays strike your retinas and launch a cascade of neural computing that constructs your perceived reality in your mind. It would seem like magic if you weren't so used to it. Light is one of the most powerful manifestations of the forces of physics because it tells us about our reality. Light, from the early years of our universe, fills space with a cosmic background radiation that tells us about the Big Bang, which is a massive cosmological preface, but we'll continue. Light from distant galaxies tells us about the subsequent history of the expanding universe. Light observed from rotating belts of stars in nearby galaxies tells us about the existence of dark matter, and light from eclipses of the moons of Jupiter told us through Old Romer and Christian Huygens. Or is that how you say that guy's name? Huygens or Hudgens? What is it?
I go with Huygens.
Huygens, thank you.
Huygens.
Christian Huygens, that the speed of light the light had a finite speed. Yet for all the power to advance science in its immediacy in our daily lives, light has presented an enigma to virtually every generation of scientists who have tried to grapple with its essence. Whether it was Descartes, Huygens, Newton, Euler, Laplace, Arago, or Fresnel, they all battled with light's ambiguity. No sooner had the wave nature of light been accepted when new controversies sprang up about what medium such it traveled through. Fresnel invented the first luminiferous ether to support light, but it paradoxically needed to be partially crystalline to support transverse polarization, while being partially entrained inside moving matter like water. This launched another long list of scientists grappling with light, whether it was Green, Stokes, Maxwell, Lorentz, Poincare, Michelson, or even Einstein. The nature of light refused to be corralled one way or another. Indeed, long after Fresnel was dead, Arago continued to wonder and worry, dreaming always of a final experiment to answer his questions. He was fortunate enough to live long enough to believe that he had seen the ambiguity end, and although he was too old to do the experiment himself, he saw the triumph of the apparatus that he had built with Fresnel in their early days at the Paris Observatory. The apparatus was the precursor to a family of later optical machines that ultimately would tame light, optical interferometers. So we'll get into some cool diagrams here as we go through the history. The problem was Snell's law. St. Michael's Church, the West Riding of Yorkshire, England, is a solid structure dating from the 1400s, constructed of yellow millstone with an imposing square tower looming over the churchyard. the rector of St. Michael's Church in 1767 to 1793, was an unimposing clergyman, short and fat, who made a little impression on those who he met casually. Yet for those who knew him better, he had a mind that raced far ahead of his time in fields of natural philosophy. John Mitchell, 1724 to 1793, was educated for the church at Cambridge Queen's College, where he later taught courses ranging from theology to geometry to Hebrew and Greek before he was appointed to St. Michael's in the town of Thornhill. Apparently this move freed up his time. Apparently this move freed up his time and freed up his thoughts considerably, because he began to write the most astonishing papers speculating on the matter of light, electricity, and magnetism that brought eminent visitors like Joseph Priestley, Henry Cavendish, and even Benjamin Franklin to his small town parish home. Mitchell was the first to recognize that the effects of earthquakes traveled outward from the source as seismic waves, and that they could be integrated, that they could be used to integrate the nature of rupture. He also invented a balance system that could measure local variations in the mass of the Earth. Due to these efforts, he was considered to be the father of modern geophysics. Yet his interests were surprisingly broad. In the field of material science, he had devised an ingenious way to construct magnets that could be manufactured with good reproducibility rather than relying on random properties of lodestones. In cosmology, he recognized that the binary stars were mutually bound by gravity, and by using statistical reasoning, he argued that they should have a high abundance in the heavens. It should have a high abundance in the heavens. In fact, about 85% of the stars are binary systems. Ooh, very cool. John Mitchell is probably best known for a paper he published in 1784 with an extensively long title on the means of discovering the distance, magnitude, etc. of the fixed stars in consequence of the diminution of the velocity of their light. Diminution.
That's it. Diminution.
Diminution. Thank you, sir. I knew that was not coming off right. Diminution of the velocity of their light. In the case of such a diminution, should be found to take the place in any form of them, and the other data should be procured from observations as would be farther necessary than for that purpose. And that is a hell of a title. Dude, that's quite possibly the longest title that's ever been written by another man. All right, in the paper, he proposed that there could be gravitating bodies of such mass and size that they would prevent the escape of light from their surfaces, making them appear as dark stars. Is this the interferometry section, or am I way off? I don't remember any of this.
This is the interferometer section. We're at the light speed section.
We're just getting
to it. It's kind of
okay.
Intro promo.
Got you. I was like, we're off in the stars talking about dark matter. Okay. Just making sure. All right, being dark, they would also be invisible. He suggested their presence could be ascertained through binary systems, which a bright star orbited a dark star. The modern reader, Mitchell's dark star, is recognized as a black hole, which are often detected through their effects on their stellar companions. What is not well known about this remarkable paper by Mitchell is that without knowing it, he opened a crack in Newton's formerly unassailable theory of corpuscles of light. Mitchell knew that from his astronomical studies that stars move with a range of speeds. According to Newton's theory of light, the corpuscles, which was corpuscle theories, he basically thought light was little quantized chunks, little particles. Stars moving towards the Earth should emit light particles that traveled faster, while the stars moving away from the Earth should emit light that traveled slower. This would look like this would be like shooting a bullet from a speeding train, adding the velocity of the bullet, or adding the velocity of the train to the velocity of the bullet, or the slower speeds relative to the stationary railway embankment. This part of Mitchell's argument would have been clear and obvious for any student of Newton's physics to understand. He then took the next brilliant step. Mitchell was familiar with Snell's law on the deflection of a light ray when it enters a transparent medium. Snell's law was named after a Dutch mathematician Wilbert Snell van Rooyen, who described the effect using the law of signs in 1621. Although it was Descartes who first published the law in 1637. Mitchell recognized that Snell's law for refraction of light by transparent materials like glass dependent on the speed of light outside relative to the inside of the glass. According to Newton's theory of particles should travel faster in the denser medium, and then this would be why the light deflects towards the normal if it enters the denser medium. The smaller angle inside the denser material keeps the transverse speed of the light particle the same. Yet Mitchell pointed out that if the light particles were traveling faster or slower, depending on the speed of their emitting body, then the angle they would make after entering the light surface, like a prism, should differ slightly, because Snell's law is a function of different speeds of light relative to the earthbound prism. It's really important. Mitchell calculated that the size of the effect, concluded that the differences of the speed of light as small as 1 part in 1,000 might be measurable. This is about 3 times 10 to the 5 meters per second, which is close to the speed of Earth as it orbits the sun. Therefore, Mitchell's speculations were not merely philosophical, but were an actual experiment that might be tried. In 1805, Francois Arago was merely 19 years old and yet to be sent on an epic journey to Spain to measure the meridian. The old meridian measurement, Shane. Should have known old Arago had a hand in that. He was appointed the secretary librarian of the Paris Observatory. He began testing methods to measure the speed of light and considering Mitchell's method of variable refraction. However, rather than attempting to find the speed of light emitting from a moving star had differing speeds, as Mitchell proposed, he decided to test the effect of Earth's motion relative to the light coming from the stars or set of stars. He observed that the position of the stars fixed to the prism at different times of year as Earth's relative motion changed on its year-long journey around the sun. To within 5 arc seconds, he observed no change in the refractive angle or the position of the stars. He presented his findings at the Institute on December 10th, 1805, but further measurements were postponed when he and were sent on their mission to Spain next year.
That's Bio.
Yeah, I meant to say that. Thank you. Your boy Bio. And a quick note about Arago. So yeah, he was the precursor to Airy's failure, where they filled the telescope completely with water to see if the refractive index would have any effect on the velocity component coming from either the Earth or the sky. And what he found using a half-covered prism, or half covering the telescope with a prism, was that he didn't have to make any further correction angles when that starlight intersected with the unobstructed portion and the portion that had the material medium in it from the prism, indicating that the starlight already comes in at that angle and the Earth is stationary. So they were going to continue that, but him and his boy Bio had to dip to go measure that meridian. 1 second, got to get some water. All right. The problem of the speed of light must have stayed on Arago's mind, possibly helping him while he was away in jail in Spain. Oh, dude, homie went to jail. Because his return to France, he took upon the experiments again. This time he used a prism with a larger angle to eliminate the dispersion while magnifying the effect. He placed the prism to that and covered half of the objective of the telescope. Then all that needed to do was observe a star through the prism, then shift the eye slightly to observe it through the objective alone, and then through the shift for the and look for the shift in the position. He placed a graduated circle within the same field of view, allowing very precise measurements of the apparent position of the stars down to a few arc seconds. The motion of Earth under these conditions would produce displacement depending on the time of the year that varied as much as 6 arc seconds. The effect should have been observable given the accuracy of the method, yet the experiments still produced a null. Dang, I didn't know that. It's interesting. Arago's measurements of the refraction on the starlight created a serious problem for the Newtonians who believed firmly that light was composed of particles. To save the emissionist theory, the ad hoc suggestions had to be given. For instance, Laplace, in his latest edition, Système du Monde, in 1813, questioned whether the eye could detect light at different speeds. Arago himself was puzzled, yet he was confident in his experimental results. He knew that if the Newtonian theory was correct, his measurements would have found the effect of Earth's motion. Thus, when Fresnel approached Arago with the ideas of his nephew Augustus about the wave nature of light, Arago was primed and ready to overthrow the emissionist, especially since he was known by then politically opposed to Laplace. The dawn of interferometry. Sometime during 2 years from 1816 to 1818, when Fresnel and Arago worked together on the Paris Observatory, Arago realized that the separated paths of Young's double-slit experiment provided an opportunity to have one path travel through air while the other would pass through the transparent material. For instance, a thin sheet of Missa would be placed over one of the slits. Go ahead.
That's mica.
Mica, thank you. A thin sheet of mica. What is that? Do you know?
It's a mineral. It has particular electrolytic properties. They use it for insulators for transistors too.
Gotcha.
A thin slice of it.
Gotcha. Okay, a thin sheet of mica that could be placed over the slits while the other slits remained clear. When Arago and Fresnel performed his experiments, they noticed that the fringe pattern shifted by a non-negligible amount. Based on whether the wave theory of light, the shift represented a delay in the arrival of the wave front at the observer's plane caused by the refractive index of the mica slowing down the speed of light. It can be argued that this experiment by Arago and Fresnel was the first interferometer because it was the first time interference was used to measure a material property. Shout out to the boys making the first interferometric measurements. Although this demonstration of interferometry was crude, it was common with many discoveries that with the new phenomenon of this, once this new phenomenon is observed, subsequent improvements more rapidly. Within a year of this simple double slit experiment, Arago had constructed a more sophisticated interferometer that could measure the refractive changes along long path lengths. Late in his life, 1852, before his death, Arago wrote in his memoir describing the interferometric measurements he performed with Fresnel in 1818 to measure the refractive index of moist air relative to dry air. This was an important question for astronomy because the changing atmospheric conditions place a fundamental limitation on astronomical observations of slight shifts in stellar positions. For instance, starlight might be affected by the change in air moisture content as a function of altitude by refracting light, causing systematic shifts in their position. As an astronomer, Arago was well aware of the possibility of the effect and sought to answer whether it could affect astronomical observations. Arago's interferometer design was ingenious. The key problem was to get two independent light beams originating from a small source to propagate parallel to each other with wide enough separation that one beam could travel through one material while the other traveled through a different material. The double slit configuration is not appropriate for this because the beams spread out widely when they diffract from the slits. Fortunately, Arago knew a lens can take light from a point source and turn it into a collimated beam that can travel over many meters without expanding. This was achieved simply by placing a point source at the front focal point of the lens, masking off the light after the lens creates a parallel pencil beams. Once the pencil light passed through the copper tube filled with moist air while the other traveled through a tube of dry air. To recombine the paths creates an interference fringe. This process was reversed using a lens to focus on the light back to a small point where the fringes could be observed by eye. The final apparatus, shown in figure 3.1, had two side-by-side slits or side-by-side copper tubes, a meter long, that were capped with equal thickness, optical quality plates. Moist air was introduced or pumped out of the tubes. A lens collimated the light for a small pinhole, and an opaque mask allowed for a beam to enter the copper tubes, propagating without reflecting from the tube walls. After exiting through the glass plates, the lens focused the two beams down to one. When the beam paths were identical, the fringes formed an output, and the moisture was pumped out of the tubes, and the fringes shifted predictably. So we'll take a look here at the first interferometer setup. So we got our light source here, hits this lens. Everything gets focused and split into two sections where it's going through a copper tube, gets recombined where they check their fringes, and these two contain different material substances inside. So the speed of light is going to be faster in one, not the other. So when these recombined, they're going to be out of phase. Figure 3.1, Arago's interferometer around 1818. The point source at S collimated the lens and passes through the two apertures. The beams traverse a 1 meter copper tube and are recombined by a second lens. Moist air could be added or removed from one of the copper tubes. The second tube served as the reference arm. Light propagating through a meter of saturated moist air suffered a fringe displacement of about a quarter wavelength, representing a refractive index of moist air that differed from dry air by about 1 part in a million. This exquisite measurement was so clever and so sensitive that it created a stir in the scientific community. Laplace, who was no great friend or supporter of Arago, mentioned several years later in his 1824 edition of his Système du Monde, writing that M. Arago, using a means as accurate as ingenious, showed the influence of humidity of air. The effect was so small that nothing other than interferometry could have measured it. But it was also so small that it removed the question of whether humidity from the atmosphere created a problem for stellar positions. It did not. Despite the obvious usefulness of Arago's interferometer from our perspective today, it was a one-off experiment answering a very specific question at that time, and then it was abandoned. Even 30 years later, when Arago revisited the experiment with the help of Armand Hippolyte Fizeau in 1819 and 1896, it was once again to measure the refractive index of moist air rather than to expand its use into other fields. The gap in the use of Arago's interferometer for nearly 30 years was part because it did not use light in a very efficiently. From a single bright light source, only two small pencils of light were extracted, and the resulting fringes were so dim that they required the extreme sensitivity of the human eye to observe the fringes in a small region where the beams overlapped. Arago's interferometer, although brighter than Young's original double-slit experiment, still rejected the vast majority of light rays. This disadvantage was later removed by Fresnel, who conceived of an optical configuration using two slightly angled mirrors that captured all the light rays and produced bright fringes. The fringes could be observed over a large area as opposed to being restricted to a tiny spot of fringe that was produced by Arago's interferometer. Fresnel's mirror in figure 3.2 consisted of two mirrors placed side by side, but with a small angular deflection of one relative to the other. We'll take a look here at what we got. So we got source, vertical source, Yeah, I have no idea what's going on there. So it's just shooting light rays from two separate sources, and then they split slash recombine
That's a
and go
two-piece mirror.
and hit the
Same
screen.
source. Like, no, that's a two-piece mirror.
Oh,
The blue and the red are
ver-
coming from source down, hitting the mirror on two angles and firing the same light in two directions off of it simultaneously.
got you. That's the path of what it would take after it hits or whatever. Like,
Yeah.
got you.
You
Got you.
create
Okay.
two virtual sources out of the same source, yeah.
Awesome. All right. Very cool. Figure 3.2, Fresnel's mirror and Lloyd's mirror. The interference fringes on the screen as phase varies linearly with height. A light source illuminated the mirrors at an oblique angle, reflecting the rays onto the screen. Because this mirror tipped at slightly different angles, they produced two virtual images of the light source that were slightly displaced from each other, filling the space with overlapping wavefronts that produced a high contrast of fringes over the large area of the screen. Fresnel's mirror was not used as a refractometer, at least not by Fresnel. Fresnel's mirror was not used as a refractometer, at least not by Fresnel, but it did provide a bright, dramatic, and easily viewed demonstration of the interference of light. 15 years later, the Irish physicist Humphrey Lloyd, 1800 to 1881, created a version that was even easier to operate because it only used a single mirror and a screen. The bright wide field interferometers were the predecessors of the holographic gratings that would become common after the invention of the laser in 1960. They also played a particularly important role in the first demonstration of the temporal coherence of light performed by the famous French duo French optical physicist. Our boy, yeah, I was thinking of Dufour and Prunet, but it's going to be these two French lads, huh? All right. Anyone want a popcorn?
Yeah, I got you.
Cool.
Yeah, Fizeau and Foucault. The French physicist Armand Hippolyte Louis Fizeau was born in Paris into a wealthy family as the son of a successful doctor. He was set on a path to follow his father into medicine, but was diverted when he took a course in optics. Armand was not considered the brightest of the Fizeau children, and he attended the Collège de France, while his brother attended the prestigious École Polytechnique. His brother took detailed notes in his own optics course that he then passed to Armand, who studied them assiduously. What started out as an intense hobby in physical optics turned into a vocation, where he began studying at the Paris Observatory under the tutelage of François Arago, who recognized an untapped talent in this largely self-taught student. Arago, by the late 1830s, had become the premier French expert on optics and optical phenomena, and was its chief proponent and archivist. He wrote and lectured prolifically, occasionally suggesting new experiments, although his own days of experimental work were long past. Following the July Revolution of 1830, the insurrection that featured Victor Hugo's famous book Les Miserables, Arago had become active in politics. Over the following 2 decades, Arago was elected and re-elected as deputy for his native department, the Pyrénées-Orientales, and later for Paris, where he sat on the left in the Chambre des Députés. He was a proponent of the educational reform and freedom of the press, as well as the application of scientific knowledge to technological progress, particularly canals, steam engines, railroads, and the electric telegraph, and photography. On August 19th, Arago gave a public lecture on a new invention by Daguerre that allowed the image formed in a camera obscura to be captured permanently on a light-sensitive plate. The daguerreotype process, named after the inventor, became a sensation that was taken up by amateur and professional scientists. Was fascinated and began experimenting. Well, you can hear me now. And began experimenting with ways to improve the contrast of the prints. Fizeau met a kindred spirit in Jean-Bernard Léon Foucault, and who also had been a weak student, but who had tremendous experimental skills and a curious mind. Like Fizeau, Foucault had initially thought to become a doctor and showed particular promise as a future surgeon, but he was repulsed by gore and suffering that accompanied that profession. Fortunately, his abilities were noticed by a professor of microscopy who took him on as a lab assistant, drawing Foucault into the study of light and optics. Fizeau and Foucault formed a close friendship and forged an informal team to study and improve early photography. Beginning in 1843, they worked for 2 years on photographic process that culminated on April 2nd, 45, in the first scientific photograph on the surface of the sun that was able to clearly delineate the images of sunspots. By this time, they had also been experimenting with interference effects, initially following Young and Fresnel, but then forging beyond with new approaches that struck to the core of the difficult physics of coherence. In November of 45, Fizeau and Foucault performed one of the most elegant optical experiments of the 19th century. Today, the experiment would be called spectre interferometry, but at that time, it had no precedent. A persistent problem with interference effects had been the extreme sensitivity of the effects to the different path lengths taken by separate interfering waves. Under the best conditions, with the brightest sources, it was only possible to detect about half a dozen fringes to either side of the main interference peak. The cause of this limitation was known to be the broadband nature of white light that was composed of many different wavelengths. When the optical path difference between two beams of light was zero, then all the wavelengths aligned in perfect constructive interference. However, when the optical path difference increased to half a dozen wavelengths, then the longer and shorter wavelengths no longer provided perfect interference, and the fringe visibly vanished. Oh, the fringe visibility vanished. There had been attempts to pass white light through the colored filters to make it more monochromatic, but too much intensity was lost in the process. Fizeau and Foucault hit upon a brilliant solution to this problem by using the Fresnel mirror to produce relative path differences while maintaining high intensity, then dispersing the interfering beams through a prism to create a spectrum. By using a set of lenses, they recombined the spectra on an observation plane that held a photographic plate as shown in figure 3.3, which we just went past there. The result was a bright spectrum spanned by thousands of fringes. Path differences as large as 7,000 wavelengths, several millimeters, could still produce interference fringes. This experiment was the first demonstration of the classic trade-off between spectral bandwidth and temporal coherence length. Not stopping there, Fizeau and Foucault extended their measurements on the long wavelength side of the spectrum by using tiny thermometers to measure the first interference effects for infrared light. They also placed polarizing crystals in the system and demonstrated the first interference fringes represented by polarization rather than intensity. These experiments by Fizeau and Foucault went far beyond the work of Fresnel, who in his own time had gone far beyond the work of Young. Fresnel had replaced Young's double slit with alternative geometric configurations that firmly illustrated the wave nature of light, but which did not delve into the questions of coherence, other than recognizing that spatial coherence was required and could be created through the use of pinholes. The work by Fizeau and Foucault launched the field of coherent optics, which today is a vast field on which vast tomes have been written. Coherent optics is a workhorse of modern optical techniques and applications. For instance, spectral interferometry is used for the characterization of femtosecond layer pulses, and it makes it possible to image inside translucent media in a format known as spectral domain optical coherence tomography. Arago, who had begun as an emissionist, must have beheld all this with some sense of wonder, witnessing within his lifetime the development of interference from the simple slits of Young through the improvements by himself and Fresnel to the exquisite demonstrations by Fizeau and Foucault. Twilight in Paris. Some years before Fizeau met Foucault, Arago had attended a meeting of the British Association of Science where he saw a presentation by Wheatstone that would prove oddly fatal to the fruitful collaboration and friendship between Fizeau and Foucault. Charles Wheatstone was a British physicist who became famous during the Victorian age for his contributions to the telegraph and especially for what is today is known as Wheatstone Bridge. In 1838, before the teenage Victoria ascended the throne, he built a high-speed rotating mirror device for the ostensible purpose to measure the speed of electricity propagating down a long wire. As soon as Arago saw it, he realized that it could be used to answer the question that had obsessed him for his entire career, the question of the wave-like versus particle-like nature of light. By 1838, this question had been firmly answered in favor of the undulationists. But the earlier battles with Biot and Poisson must have left a mark because Arago still yearned to make the decisive experiment to answer this question beyond a shadow of a doubt. Based on the old battle between the emissionists and the undulationists, it was expected that if light were a wave, then it should travel faster in air. But if light was a particle, it should travel faster in water. The only measurements on the speed of light up to that time were astronomical, for no one had devised a method to measure the speed of light terrestrially, and certainly not in a lab. When Arago returned to France in the summer of 1838, he gave a public lecture in which he proposed to use the rotating mirror to make direct comparison of the speed of light through air versus water. At that time, such a public declaration represented the claim of priority for the idea, and Arago had every intention of carrying it through. Not held hostage entirely to his political life, Arago built a prototype for his proposed apparatus and attempted to perform the experiment in 1844, but the results were ambiguous. By this time, Fizeau working with Arago for several years, and it was the same year that he and Foucault began working on the daguerreotypes. Therefore, ideas about experiments to measure the speed of light directly in a terrestrial setting were never far from the minds of all three scientists. Unfortunately, the spinning mirror experiment proposed by Arago had an optical configuration that made calibration very difficult, putting the experiment on hold. Several years later, in 1848, Fizeau had a flash of insight into how to measure the speed of light directly without spinning the mirror. This was not the experiment that Arago was most interested in. Arago wanted to compare the speed of light traveling in air relative to water, but it would represent the first terrestrial measurement of the speed of light in air. The idea was surprisingly simple, using a spinning toothed wheel instead of a spinning mirror. In Fizeau's design, illustrated in 3.4, the teeth of a spinning wheel would periodically block a beam of light as it reflects off a distant mirror and returns along the same path to the observer. Because light takes a finite time to propagate, if the wheel is spinning fast enough, an open notch for the outgoing beam will have shifted sideways so that an opaque tooth now blocks the return beam. At higher speeds, the returning light would pass through the following notch and become visible again. And even at higher speeds, the light would be blocked yet again by the next tooth. By measuring the speeds at which the returning light becomes visible or is blocked, given the distance to the reflecting mirror, one could merely measure directly the speed of light in air. Because the idea had been Fizeau's alone, it was understood that he would work on the experiment without involving Foucault. This was a collegial decision that should not have sparked jealousy, except for an unfortunate twist. In January 49, just before he began working on his speed of light experiment, Fizeau was elected to be a member of the prestigious Société Philomatique de Paris in recognition of the work he had done with Foucault on the daguerreotype, as well as on the uses of photography and telescopes for astronomy. and for the elegant spectral interferometry experiment, also with Foucault. Foucault was thrilled for his friend and collaborator, in part because he was next in line for election to the Société later that summer. It had been the custom for the second-place candidate to be selected in the following election. However, the next election committee did not follow this tradition and passed over Foucault. This slight may have been Foucault's main occupation when he wasn't in the lab, was as a science reporter for the French magazine Journal des Débats, where he was called on to give his opinions of the latest discoveries. He was sometimes less than complimentary, penning critical reviews that at times called experiments uninspired or pedestrian. These reviews may have built up resentment against him, and some of his targets would have been members of the Société. Regardless of the reason, the snub by the Société fell hard on Foucault, who withdrew in disgust, and he may have fallen into a depression, for he disappeared from sight for nearly 6 months. It was during Foucault's absence that Fizeau completed his speed of light measurement. Through the spring and early summer of 1849, Fizeau set up his experiment to cast a beam of light from the rooftop of his father's house in Suresnes on the west side of Paris, directed to a telescope mounted in a telegraph station on the hillside of Montmartre, where the focused beam was reflected by a mirror back through the telescope, retracing its path to the rim of the spinning tooth head wheel, where the return light was detected by eye. The total distance traveled by the light beam was an astounding 17.266 kilometers. The experiments were performed in Paris twilight, when it was just light enough to enable the beams to be directed to their dimly visible targets, while just dark enough to enable the extremely faint reflected light to be detected by a dark adapted eye. After months of struggling with the difficult optical alignment, the experiment was successful. On July 23, 1849, Fizeau reported his findings to the Académie des Sciences. He had measured the speed of light in air to be 315,300 kilometers per second, close to the previous value obtained astronomically. Fizeau received great acclaim, recognized for accomplishing one of the most important yet difficult experiments in the physics of light. 4 months later, Foucault was belatedly elected a member of the Société Philomatique. Fizeau was on the selection committee, and he returned to his post at the Journal des Débats, where his first article praised Fizeau, proclaiming that he has sometimes been lucky, I concede, but is the same luck that supplies rhyme to the poet and discoveries to men of genius. It is not known whether Fizeau was pleased with being called lucky, because the design and hard work he had to put in the experiment had nothing to do with luck. At the beginning of 1850, it would have been natural for Fizeau and Foucault to have turned their attention to the experiment that Arago considered to be the real point of the speed of light measurements, determining the relative speed of light in air versus water. Experimental plans had hit a wall, because a direct measurement of speed, like that done by Fizeau, was not accurate enough to measure the difference over short lab distances. Arago's design of the spinning mirror also had a fundamental alignment problem associated with the fold mirror. Once again, Fizeau had a flash of insight and understood that the problem was because the fold mirror was flat. But if it were a curved concentric mirror, then the misalignment could be zeroed out. Such an insight, removing a barrier that had stood in the way for more than a year, collaboration move ahead smoothly with the main experiment. However, as Alfred Collineau, the French physicist who was a protege of Fizeau, lamented years later, the day Fizeau had the idea of the concentric mirror was the last day of the collaboration. It started a steeplechase as Fizeau and Foucault each forged ahead on their own to make what they thought would be an historic measurement that would stand in the annals of science for all time. The specifics of why the two scientists fell out have even been lost to history. A flurry of heated letters filled with recriminations went back and forth with Fizeau and Foucault during the last days of the competition, but the original cause of the split is unknown, and neither Fizeau nor Foucault ever spoke of it later through their long careers. One possibility is that Foucault may have made a faux pas in perceived etiquette with respect to Arago, unlike today when any scientist can take inspiration from another and perform any experiment without reproach. In the polite days of the French Académie, there was a tacit ownership of experimental ideas. When Arago outlined his experimental design to test the speed of light and air relative to water, he had staked his ownership. Even if Fizeau and Foucault helped him with the experiment, it would have been understood that the experiment was his and he should have first shot at performing it. However, by early 1850, Arago was losing his eyesight because of diabetes. Tough break, bro. It must have been a severe disappointment to him, not only because of the difficulties it caused him personally, but also because it prevented him from completing the central experiments that had obsessed him for nearly his entire career. At just this delicate moment in his life, Arago received an unexpected visit from Foucault, intending no disrespect, and indeed because he respected Arago so highly. Someone's hot micing pretty bad there.
Got it.
Foucault felt bound by honor to inform Arago that he wished to move ahead to complete the experiment by himself. Arago must have been taken aback. Foucault did not seem to be asking permission, but was merely informing Arago of his intentions. Arago would have understood that because of his own failing eyesight, the experiment was no longer within his power to accomplish, so he grudgingly gave Foucault his approval to proceed. What motivated Foucault to take this bold step? Is it possible that he felt his own career was being eclipsed by Fizeau's recent success and fame for his measurement of the speed of light? It is possible. Or he may have been bruised by having been overlooked initially for the election to the Société Philomatique, although he was now belatedly a member. On the other hand, as a master instrument maker, he had conceived of a mechanical device that radically improved upon Wheatstone's spinning mirror, enabling it to spin at a much higher rates with much greater stability, just as Fizeau's novel idea of the toothed wheel had allowed him to perform his speed of light experiment without Foucault. Perhaps Foucault felt that this new design of the spinning mirror gave him the authority to do the experiment without either Fizeau or Arago. Foucault implemented his new spinning mirror system using a steam-powered turbine that spun the mirror at an astounding 200 rotations per second. Despite the small size of the mirror, the centrifugal force was so great that it caused the mercury amalgam used at that time for mirrors to separate from the glass and splatter across the experimental benchtop. This forced a stop to the experiments until Foucault devised a method for depositing a sturdy layer of silver on the glass mirror. This method of silvering a mirror was to have great significance in the later development of interferometers by Michelson and others. With baffles placed around the experiment to protect the optical elements from oil and steam flying off the screaming turbine, Foucault got a first glimpse on February 17th, 1850 of the success of his ideas, though he still had several months of hard work ahead. Around this time, either because Foucault shared his progress with Fizeau or because Arago had informed Fizeau of Foucault's strange visit, Fizeau realized that he was behind in the race. Arago had previously enlisted the help of his personal instrument maker to build Wheatstone's spinning mirror system for his own planned experiment. So he now loaned the apparatus to Fizeau to help him compete against Foucault. However, Foucault's design was superior, enabling him to move faster and approach the ultimate goal. And by April 22nd, Fizeau was in a panic. He sent Foucault a rambling, long letter scribbled in crayon, accusing him of a great insensitivity and misconduct. I think he should have used felt pen. Foucault's response was short and polite, written in clean ink penmanship, begging Fizeau to calm himself and not to take such offense. Fizeau replied with yet another letter, incensed and clearly viewing himself as the injured party. And on April 25th, the two longtime friends and collaborators split, unable to achieve a rapprochement. They would never work together again. Oh man, it's like
That's
the Beatles.
so heartbreaking, bro.
2 days later, on April 27th, Foucault's experiment was a successful thing. His two light paths, one through air, another through a 3-meter-long pipe containing water, with glass flanges at the ends, displayed different displacement at the observation port. One image was shifted slightly to the side of the other in just the right direction to finally and definitively put to rest the emissionist theory of light. Light was composed of waves. Foucault was so excited and so awed by the historical importance of the experiment that he had 3 individuals peer into the viewport to confirm the results. Somehow, Arago must have heard the news, because 2 days later, on April 29, he gave a strange speech at the Académie outlining the history of his idea for measuring the relative speeds of light in air and water. He reminded those present of his original experiments many years before with Fresnel on the first interferometric measurements of the refractive index of dry air relative to moist air, but how this had contained an ambiguity on relative speeds, motivating his idea for a direct experimental test. He mentioned Foucault's name, who was sitting in the audience, but he did not mention his results. The next day, in a short paragraph in the Journal des Débats, Foucault announced that he had succeeded in making the experiment. Then on May 6, 1850, he officially reported the results to the Académie. His mirror had achieved speeds of up to 800 rotations per second, producing deviations of 300 microns, measured by observing the shift using a thin fiduciary ruling between the 2 light beams passing through the air relative to water. Fizeau followed Foucault by reporting that he too had constructed an apparatus that performed as required, but that the lack of sun had prevented him from making the measurements. At the end of his presentation, he made the excuse that he had been delayed in starting his experiment because he had waited for Arago to authorize us to embark on a topic of research which belonged to him. This barb was clearly aimed at Foucault and his perceived indiscretion. It took Fizeau 7 more weeks before he could report on his own experimental findings, but by then he had lost both the priority and the fame. The aftermath of Fizeau and Foucault affair is mixed. The importance of the air versus water experiment that loomed so large in their minds is actually a side note in the history of science. By 1850, the emissionist theory of light was already dead, and only Arago was left worrying about the final proof. Foucault certainly believed that this experiment would be his legacy, making him immortal, which is probably why he was willing to step over the line to achieve it. Yet, from our 21st century perspective, it is Fizeau's original experiment on the speed of light that stands out. That is how he achieved his own immortality, even though his later interferometric work may have been more influential for the ongoing process of science. For Foucault, on the other hand, the pendulum that he demonstrated a year later in the Pantheon in Paris cemented his name into history, even as his experiment on air versus water has all but faded from memory. Anybody want to read the last 6 pages? Or shall I just keep going? I'll just keep going. What the hell? Interferometry comes of age. Fizeau understood that the deep complexities of the coherent properties of light better than anyone else living. For instance, as early as 1848, he proposed that light from a moving source would be detected at shifted wavelengths in a spectrometer. This phenomenon is the Doppler effect, named after Christian Doppler, who had proposed the effect 6 years earlier in a small meeting of the Bohemian Society in 1842. Doppler had thought that the effect would make stars change color, while Fizeau correctly pointed out that the shifts would be detected in the change of wavelength of narrow spectral lines. The effect of Doppler Fizeau now underlies the most sensitive astronomical measurements of motions across the universe. Proposed additional astronomical applications of interferometry, as we will now explore in Chapter 6 on stellar interferometry. Yet, the experiment that he's most famous for, after his measurement of the speed of light in air, was his measurement of the speed of light in moving water. This was not merely an incremental advance on his earlier experiment. Because 50 years after Fizeau completed the experiments, his results would provide the central evidence that Einstein would use to abolish the ether entirely. Fizeau's experiment to measure the speed of light in moving water is shown in Figure 3.5 as a modified form of Arago's interferometer. The light source is partially reflected by a glass plate to pass through the lens located one focal distance away from the source and is split by an aperture mask into two pencils of light. A pair of rectangular prisms separates the pencils so that they can pass through the flow apparatus composed of two tubes. Water is introduced into the one side and expelled on the other, creating two oppositely directed longitudinal flows. You guys want to take a peek at that 3.5 for a sec? Go right ahead. Yeah, fair enough. It does look very similar, doesn't it? All right, the pencil of light traveling down one tube is moving with the flow and is moving against the flow in the other tube. After exiting the glass flanges, the beams are focused to the mirror that redirects the beams back to the lens that recollimates them and directs them down the opposite tube. The two beams are combined at the observation point, labeled O, where the interference fringes are observed. One pencil of light travels with the flow in both arms of the interferometer, while the other pencil of light travels against the flow in both arms, doubling the effect at O, which is the observation point. When the flow rate was 0, Fizeau saw the fringes in one arrangement, but as the flow increased from 0, the fringes shifted laterally in the viewport, and the amount of lateral shift was directly proportional to the speed of the water. Fizeau then reversed the flow, doubling the measured effect. When water was flowing at 7 meters per second, he observed nearly half a fringe shift between the case for flow in one direction versus the other. This half fringe shift was consistent with a theory that Fresnel had constructed based on the partial entrainment of ether by moving matter, deriving a quantity known as the Fresnel drag coefficient. He had constructed this theory to explain why Arago's measurements of the motion of the Earth using starlight observed through glass prisms had yielded null results. The partial drag of ether by the glass prisms precisely cancelled the effect first proposed by Michel. Therefore, Fizeau's results ruled out other hypotheses of complete ether drag as well as completely immobile ether. Fizeau, recognizing the importance of his results, published immediately. 50 years later, when Einstein was formulating his new view of relativity, he was inspired by the positive experimental results of Fizeau from 1851 more than by the null results that Michelson and Morley would obtain in 1887. In Einstein's hands, Fizeau's experimental results provided support for the relativistic addition of speeds. When Fizeau published the results of his ether drag experiment, French experimental optical physics was entering a new and extremely productive phase of research on the physics of light. Fizeau and Foucault were among the last of a genre of serious amateurs who were mostly self-educated outside the university system. At the time when they were working in the 1840s and 50s in Paris, a similarly self-taught scientist, Michael Faraday, was at the peak of his career at the Royal Institution. However, in both France and England, young university-educated academics began moving into the top teaching and research positions. They were professional scientists, and their status often eclipsed their older autodidactic colleagues. For instance, when Foucault was passed over for election, to the Société Philomatique in 1849, the event that so disturbed him that he dropped out of public view for half a year, the person who took his slot was Jules Jamin, a student prodigy at the University of Reims, winning many academic awards and going on to take his first position at the Collège Bourbon in Caen in Brittany, where fundamental experimental studies of light reflection from metals gained him his election to the Société Philomatique over Foucault. Jamin was married in 1859 and had 2 children, his daughter later becoming the wife of Henri Becquerel. 1852, Jamin obtained a coveted position as a professor at the École Polytechnique and taught the course in general physics, publishing his lecture notes in 1886. It was an influential physics textbook that helped educate the new generation of French physicists at the end of the 19th century who would help usher in 20th century modern physics. Jamin continued his experimental studies of light and optics at the Polytechnique. He was inspired by the work of Arago and Fizeau on the interferometric measurements of the refractive index of gases and began to view these measurements as examples of a larger class of measurements that today we call refractometry. He was aware that the point source and double slit masks that Fizeau and Arago had used were inefficient, making the interference fringes very dim. Although Fizeau and Foucault used the Fresnel mirror for their long path difference interference experiment to solve this problem, the double set of mirrors were difficult to align. And in 1856, Jamin conceived of an ingenious new refractometer that had high brightness and was easy to align. The new design dispensed with the double slit configuration and its relatives that had dominated almost all prior approaches to refractometry. There we go. Jamin knew that the light transmitted through a glass plate produced a weak reflection of approximately 4% from the first surface. This partial reflection was usually considered a parasitic effect that degraded image quality in optical systems by producing ghost images and glare. Jamin flipped this undesirable background problem to become a new way of performing refractometry, creating what is today is called an amplitude splitting interferometer. The Jamin interferometer, shown in figure 3.6, consists of 2 thick but extremely flat plates of glass that are silvered on one side. A pencil of light is incident at 45 degrees on a first plate of glass and is partially reflected, path A, and partially transmitted, path B. The transmitted wave is completely reflected by the silvering and exits the glass plate parallel to the first pencil of light, but shifted laterally so that the 2 pencils of light are formed that co-propagate. The 2 that are formed co-propagate toward the second glass plate. The first pencil of light, path A, is transmitted into the second glass plate and completely reflected by the silver. As it exits the glass plate, it is perfectly superposed on the partial reflection of the second pencil of light from the first plate. An exit mask ensures that only the superposition of path A and path B exits the apparatus. The design is ingenious because at the exit mask of the interferometer, both beams have traveled exactly the same optical path length, assuming the plates are identical and have equal intensity. This is the perfect condition to produce high contrast interference fringes to the eye, or photographic plate. To perform as a refractometer, one simply placed a material in one of the 2 paths to observe the shift in the fringes. The importance of Jamin's work was recognized immediately, and 2 years after publishing it, Jamin received the Rumford Medal from the Royal Society in Britain in 1858. This prestigious award had been endowed by Benjamin Thomson Count Rumford years earlier for an outstandingly important recent discovery in the field of thermal or optic properties of matter made by scientists working in Europe. Jamin's amplitude-splitting interferometer introduced a new class of refractometer that would culminate over the next half-century in a vast menagerie of wildly different forms of interferometer, including the most iconic interferometer of them all, invented by a child of the California gold rush, the Michelson interferometer. And that's the end of the chapter.
Nice, dude. Thanks for taking over there. What a great, rich history.
Everybody's still awake?
Yeah.
Yeah, I think it's crazy how scandalous some of these
Damn, he's
early
loud.
science rushes were.
Whoa, dude, you woke me up. Hold on, like you just screamed into my brain. Why is Galatrax so loud?
I'm whispering.
Oh, he's back. Oh, I'm like, okay. You're back home
Check
at
your
your
volume sliders.
Yeah, you're back at your house or whatever.
No, I'm
Got it.
not. Actually, I have to spend the night at my mom's house because I'm doing like dentist stuff.
Okay, well then I have no idea and I can't predict anything.
But it's crazy how like scandalous these like early science rushes were. Like the crayon letter.
Yeah, I really liked the crayon part. That was very entertaining. How do you know this guy has become unhinged?
You know, as a child, I had this impression. I mean, actually, all the way, I think maybe until I became a flat earther, I had this impression that scientists were so dedicated to truth and science and knowledge that they never allowed petty emotions like, competitiveness and jealousy, or, things like that to ever get in their way. And I think this is because my mother's grandpa, he was a fellow of the Royal Entomological Society. So that's, he studied bugs. And and I think I was left with the impression that these people were, kind of like how she spoke about my great grandfather, her grandfather. So I was very naive to think that scientists, for the most part, they're pretty much just as human. I always thought of them as like their first love being truth and knowledge, but really they succumb to ego just as much as anyone else. So that's disappointing.
Yeah, I think Danielson fell asleep too. I just unmuted him. You just hear him snoring.
That's a mean snore. I thought he was Gonzo for a second.
Can you guys hear my wife on the couch?
Yep,
Yes,
I could hear the whole time you were reading. Yeah.
It's harsh, isn't it?
Well, no.
She's still snoring right now.
It sounds like she's snoring at about 30 feet, which is like tolerable, right? Not like right in the mic.
Would you believe 8?
No, sounds like 30. I'm gonna go with 30.
Fair enough.
Daniel, what the hell, Daniel? Oh, you fall asleep? Did us making fun of you falling asleep wake you up?
The immediate social pressure and shame start sinking in.
He's like, oh fuck. People are looking at me.
We want handwritten letters in crayon.
Dude, I mean, everyone hot mics through our stuff. Dude. Ken loses his lighter every time we have a live stream. So
No, it's all good. But speaking of crayons, Lily, didn't you say that you were looking for a new coffee to try?
Yeah, well,
what?
I think I will look up at the menu and see which one I can find. But I do have a testimonial. So the other morning it was still dark, and I made myself a nice hot cup of coffee, and I was sitting there on the front porch, and all of a sudden I see this light, and this light was coming closer and closer and closer. And then it turned out to be like this UFO, and it landed right in the yard. And then out comes this little creature about 4 feet tall, maybe 3.5, and a companion about the same size. And they were gray with big buggy eyes. And I was too fascinated to even be scared. And they came up to me, and then they just made some funny sounds. But I understood it telepathically. And they said, "Ma'am, what is that lovely smelling beverage you're drinking?" And
Oh, that's Marklar.
I know. So I just told them it was brushtail coffee and that it was Ethiopian and it was really good. And so they put their hand out and they were really big, long fingers. So I thought he wanted some, or she, couldn't tell. And so I ran inside and gave them some of the coffee. So I need to order some more. Yeah.
So
So that
you
was my very first encounter with ETs.
wow. So you encountered ETs and you gave up the last of your brushtail to share it with them to make interstellar peace with them and save our entire race.
Yep. Yep.
Wow.
You guys can thank me later.
Dude, thank you. Shout out to Lily for being the ambassadress and handling that for us. And shout out to Toby for making delicious Ethiopian coffee roasted when you order it and not a day before. Why would you get coffee roasted before you ordered it? That sounds like something a psychopath would do. So if you're not a psychopath, go to brushtail.coffee and order from there, and you'll get coffee that's ordered from the day that you order it.
Coffee to the rescue yet again.
I just want to say that even if you're 4'7", you're not a little creature, as Liliana put it. You can still order brushtail. Don't want to split the market there.
Do you have like 3 gobstoppers in your mouth?
Yeah, he had oral surgery. He had a jaw replacement today.
No shit.
Yeah. All right. Well, I'm going to close out here, and then we can figure out what happened to Galatrax's jaw piece. So tomorrow, check out Flat Earth Fridays episode 119. I'll be streaming that. Shane will be streaming it. Starts at 8 allegedly. So, stay tuned for that. And then Saturday, I'll be hanging out with Jaren at 3 p.m. Eastern on his VIP thing. So if you're a sub to Jaren, check that out. And then later that same Saturday, Shane will be doing a presentation with the Ether Cosmology Internationale Communauté, right? That's our international Czech division, sorry. And so Shane's going to be doing a presentation on maps and coordinate systems, the old Graticule. So definitely check that out. We'll be streaming that as well. And there'll be a translator for the Czech lads. It's going to be awesome, similar to the thing that we did a week or two ago with relativity theory. And then on Tuesday, Dr. Bennett will be joining us to go over Einstein's little thought experiment regarding a certain train and simultaneous lightning strikes with respect to moving observers and stationary observers. So that'll be really fun to go through and dissect all that. We're going to be going over some, the common relativist arguments and all that. So definitely tune in for that. And then we'll restart the whole cycle again and do another research and reading night that following Thursday.
I think they called it Mappy Projecta e Graticuli. I'm pretty sure that's how you pronounce it in Czech.
Oh, nice. Le Graticule, eh?